welcome again. Today, our speaker is Przemyslaw Mikolajczyk from Warsaw University. He's a PhD candidate in Wroclaw University, and he did his master and bachelor degree from the same institute. But since 2021, he has been working as an independent engineer and technical employee at Warsaw University Faculty of Physics. So today he will give us a talk titled Stars in the Observations of Tess Satellite. Dr. Mikolajczyk, thanks for accepting to give the talk here. Please, you can start.
Hello, everybody. Good afternoon. First of all, thank you very much for having me. It's a pleasure to be talking to you today. Thank you for the great introduction. I will just like to elaborate a few things more about myself. I did my bachelor's and master's at the University of Wroclaw, and now I'm the same university, a PhD candidate. So hopefully, fingers crossed, next year I should finish my thesis and defend it. My supervisor is Professor Dr. Habilitowany Andrzej Pigulski, and my thesis basically deals with pulsations of upper main sequence stars, mostly O and B type. And all this, maybe not all, but most of the data that I will and am using to write my thesis are coming from satellite observations, such as Tess satellite, which will be presented today, but also from Gaia satellite, Bright, and Coriolis satellite, which wasn't really designed to observe stars, but there was this instrument that allowed to also take even 10 or 12 years time series of brightest stars in the sky. I am also the member of Polish Gaia team under the supervision of Professor Łukasz Brzykowski from Warsaw University, and I'm a project member of BHTOM. And this is the portal designed to allow people from all around the world, which have their own telescopes, to upload feeds data to image data to this portal and get the photometric measurement. And I'm the person responsible for that photometric processing. I think that some Turkish telescopes are also part of already part of BHTOM, and I think this COMU telescopes, and as well as one in Eastern Turkey, one robotic telescope in Eastern Turkey as well. I've been observing sky for better part of my life, but since 2014, I did altogether about 350 nights in Poland mostly, but also in Chile, Greece, and Italy. I would also like to direct your attention towards the project ALPS, which is All Sky Light Portion Survey, which we started in Wrocław. And this project is aimed to preserve night sky by measuring and surveying it with photometers, as well as all sky cameras. All right, so now to the point of my talk. I will start with variability tree, with three of variable stars from ARM of Lavi. And as we know, there are many variable stars in the sky. Also, here we can see that there is plenty of different types of variability. We can divide this tree into two main branches. First one is extrinsic variabilities, such as eclipses, rotations, and so on. And the intrinsic variability, which comes from the physical processes, either coming from the stellar depth or from the stellar surface. I will be focusing today on three different variability types, four different variability types. First will be eclipses and rotation, which can be observed in Mercury-Manganese stars due to their rotation. And the second one will be the intrinsic type of pulsations. Of course, I have encircled here two different variability types, which is beta Cephei and SPB stars. But in their depth, they're basically the same variability type for different masses of B-type stars. So we know that stellar pulsations are right now a well-studied phenomenon for a better part of last 2 centuries, but only the last few decades allowed us to compute and to resolve different modes of stellar pulsations. Of course, we have the simplest example of this, which are radial pulsations, which just go along the radius of the star. Star will change its size slightly and its surface temperature, which will manifest itself in the total luminosity of the star. Of course, such radial pulsations do not, we cannot observe them in all pulsating stars. Sometimes the pulsations that we observe may be non-radial, and there are many different examples of these, depending on the complexity of spherical harmonics equation. Here are some simple movies from Concolly Observatory, which demonstrate how complicated this geometry of pulsating stars may be. Of course, only recently we have been in the possession of instruments so precise that we can resolve higher degrees of pulsations. So far, we've been facing the problem that the precision wasn't good enough, and the longer exposure times for taking the images of the stars caused averaging effect on the observed surface of the star, which in consequence played the role disabled us to resolve high degrees of pulsations. So when you take a look at the HR diagram, and we map all the or most of the known variabilities, stellar variability types, pulsation types of stars, we can clearly see two distinct features in it. First is the classical instability strip, which is inclined to the main sequence of stars. And this is the place where stars like Cepheids, classical both, and type 2 Cepheids dwell. Maybe with the distinction of these Alphautauri stars, which are kind of can be divided into 3 different classes, and only one of them really fits into the classical instability strip. But the second very interesting feature in it is that the stars can also pulsate, still living their life on the main sequence or really close to the main sequence. And such stars are, as I mentioned a few months ago, beta Cephei stars, which are mostly B2 and B3 spectral type stars, and SPBs, which are the B8 and B9 stars. Also, delta Scutis are located in the main sequence, close to the main sequence, but this is the matter of stars which have much lower temperatures. Okay, so I will now focusing on beta Cepheids and SPBs. And the matter is that we have known this kind of pulsations for quite a long time, since the beginning of 20th century. I think it's 1905, Frost found first of such class, first star of such class. But for the more than 75 years, we were unable to really say why these stars pulsate. What is the physical mechanism that exerts the pulsation in the stellar interior? We knew that delta Scutis and Cepheids are pulsating like a heat valve pump, like a heat engine, more precisely Eddington heat engine. And then there is some layer inside of the star that has the opacity just right to keep the radiation inside, and then to, in consequence, cause the entire star to expand and then to cool down and to repeat the cycle. But the breakthrough came in the 90s when new opacity tables for chemical elements appeared, and OP and OPAL projects brought new models which really showed that it is exactly the same mechanism as for classical Cepheids and for delta Scutis, but the layer, the chemical element responsible for providing electrons, giving the opacity for to this process, is not helium, it's not hydrogen, but elements from the group of iron, mostly iron. And some 200,000 kelvins inside the star, there are something called Z-bump from the metal group, which very plainly and very well explains why those stars may have unstable pulsational modes. Okay, right now a little bit about Tess Observatory. I'm sure that everybody of you know quite a lot about that, but I think this is the right time to just say a little bit. Tess was designed to continue the work of Kepler, but this time to survey the entire sky with unprecedented precision, down to parts per million, 200 or 400 parts per million, depending on the exposure time, in search of exoplanet transits in front of stars. But as we know, such a survey will give us a lot of data just for variability searches, for variability studies among all the targets that the satellite is observing. Tess consists of this very wide field of view. The whole camera is actually 24 by 96 degrees, and one of such CCD chip is 24 by 24. So it is in essence a great surveyor of the whole sky, and thanks to the fact that it is observing a slice of the sky for about a month, for 27 days, it will give us a very long time series to then analyze and look for variables, stellar variability among objects observed in this field of view. Tess is comparing to Kepler much more red. Kepler was, of course, designed to observe this little, not so little, but it's exact field of view in northern sky. So its transmission band was more blue, and you can see here in the right panel what is the difference between these two instruments, between these two telescopes, and corresponding spectra for G dwarf and M dwarf. Of course, this also supplements the fact that there are a lot more M stars in the sky than G stars or even K stars. And also Kepler, as well as Tess, the bandwidth, the band designed for these telescopes is very wide, up to up to Sloan Z band, which basically is being cut off by responsiveness of silicon. Okay, so having said all that, one problem will arise very quickly. What about the image resolution for these observations? We have in one chip 24 by 24 degrees, and these chips are 4K bar 4K. So the pixel scale for each pixel is about 21 arc seconds. It's more or less the pixel scale of ASA's project. Yeah, that means that a lot of different variability sources, a lot of stellar sources will be dwelling in one pixel. And this is a real problem. And you can see here in the left panel what Tess sees comparing to what DSS survey sees for the same field of view. And this particular field of view is in the southern hemisphere, in the vicinity of open cluster NGC 6200. So if we want to study clusters, it will be really tough, because not a lot of members will have their own photometry, and all the faint objects will just disappear. Bearing in mind that Tess can see targets up to, let's say, 14, 15 magnitude bright. Okay, now coming to the chemically peculiar stars. First thing I would like to say that they can be divided into 4 different classes. If we really would dwell on it, we could divide them quite differently, and maybe to more classes, but 4 different classes depending on the effective temperature of these stars. First one is AM stars, which are metallic strong lines present in the spectrum. Second, AP stars, so this well-known chemically peculiar stars, which have overabundant strontium, chromium, europium, and silicon. And these stars are a little bit hotter. And then we come to B stars, the late B stars, which have mercury and manganium very much overabundant in their spectra. And these stars are also very slow rotators, which has sign I with about less than 75 kilometers per second. The fourth class would be helium weak stars, and these stars are of course much hotter, coming to about early B spectral type. And when we take a look at those 3 classes, we take 3 classes of peculiar stars here visible in the right panel. The middle one is for HgMns, and in the left panel we have the HR with pulsating stars overplotted, and those peculiar stars also visible. Then we can clearly see that BP stars kind of overlap with SPB stars, and also HgMn stars are close to the region where SPBs dwell in the main sequence, in the upper main sequence. So we would expect that some of these chemically peculiar stars will be pulsators. So the brief characteristic of HgMns is that surface abundances can depart by many orders of magnitude from values for our sun. This is a quite common effect, and may be observed about 20–30% of all B, A, and F main sequence stars. And all these peculiarities come from atomic diffusion, which is greatly modified by gravitational settling and radiative acceleration. It comes from either from the existence of a secondary component in the stellar configuration, or from the existence of strong magnetic field, or effects like inclined rotation and so on. In outer parts of late B and early AA stars atmospheres, these chemical anomalies are likely to arise because the convection is not so effective in such stars. And there is also no rapid mass loss like in O stars and WR Wolf-Rayet stars. We knew for a long time that some of these chemically peculiar stars are variables, as well in spectroscopic domain as well as in photometric domain. But the proper survey has been conducted in the last 15 years, and many A and F stars are really showing pulsations of delta Scuti or gamma Doradus, or hybrids of these two types. And given that HgMns are B7 to B9 main sequence up to giants and subgiants, we would expect that these pulsations would also be visible in such stars. And domains, the pulsational instability domains, were described first by Pamiatnik in the 1999, but then Szewczuk and Daszyńska-Daszkiewicz in 2017 showed those domains also for stars which rotate. And we can see this instability domains here in the right. And as you can clearly see, there is a lot of SPBs, not only close to the terminal HgMn sequence, but also very close on even before the edge of zero HgMn sequence. So most stars, maybe not most, but some stars in this domain should be pulsators. And in 2003, Turcotte and Richard showed that about 50% of HgMn stars in the instability strip of SPBs should pulsate with the approximate amplitude of 10 millimagnitudes. Of course, this is very low amplitude. We can detect it having a very long time series for a given star. But right now, having Tess, which has perfect precision for such studies and a great observational base of the entire sky, we should be able to see many of such stars in the sun. And here is the same region of the HR shown in the Turcotte and Richard, which clearly shows HgMn stars fitting perfectly inside the instability domain. Okay, so now let's go briefly through what we did with the Tess observations. So firstly, we took all the catalogs that contain HgMn stars, beginning from Schneider 81 through Ranson and Manfred 2009, Gazarian and Alessian 2016, and the newest one, SDSS at Apogee survey, which was conducted for the better part of the last decade and compiled by Chojnowski in 2020. And this one consisted of 260 new HgMn stars. Of course, all of these studies are spectroscopic. And I will also show you today what we are doing right now, which is new 157 stars compiled from two newest catalogs, Pounsen 2021 from Lamos observations and the fourth data release, and Gonzalez 2021, which is another catalog. Then they found about 20 new HgMn stars. So from excluding the newest 157, we found that out of roughly 500 stars, test data exists for 275 of them. Of course, the cutoff comes from the fact that some of stars are not bright enough, or they are just blended in very dense stellar fields. Then we downloaded all of the data that was available from Tess in 2-minute or even the better one, 20-second cadence. And for the remaining over 200 stars, we performed FFI photometry, which respectively to the better cadence comes with 30 minutes and 10 minutes data. And altogether, we found that 188 stars have good quality time series photometry. All the other ones we discarded because we found that there are only instrumental trends visible in the data. And number of photometric measurements for each star varies from 1,200 up to 30,000 points plus. Some stars have 60,000 because they were observed for longer time in more test sectors. Of course, we compiled a HR diagram or a color magnitude diagram using Gaia data. Here you can see in the left panel still Gaia EDR3. Last Monday, exactly a week ago, the DR3 data was released, and we are right now working on compiling such CMD for the entire sample, including the new 157 stars. Effective temperatures and the luminosities are computed using parallaxes from before mentioned EDR3, and models of evolution were taken from Paxton, which is basing his data on MESA code, and opacity tables both for the old sample and for the newer sample comes from the opal opacity. We have adapted convective core overshooting to about 1.6% from Hubrig 2000. And here you can see the chemical abundances for the stars from Gazarian Alessian. And clearly you can see the cloud of overabundant manganium, overabundant mercury here in about atomic number 80. So most of them, all of them are overabundant, but most of them are hugely overabundant, but a factor of 4, right, in logarithm. For the newer survey from SDSS, this is also visible in manganium and other elements as well. So these are really strong lines, which shouldn't be here for B-type stars. So what we found with this first study is that 90 stars are variable in total. This variability comes from many different types. The nature of most of them comes from the magnetic field present in the system of 2 stars or more, or so something like alpha squared Canum venaticorum stars. There are some binaries. There is a visible rotational variability coming from the presence of chemical spots of on the surface of stars, but this wasn't really what we were looking for here in the study. But also we found some pulsations, 24 candidates for pulsating stars, but sadly only one of them is a really strong candidate for SPB. And here I will present the detailed analysis of this one candidate. HD 29589, which is 93 Tauri, is this star which is clearly overabundant in both manganium and mercury. And this is a very bright B8 subgiant star. And this was observed up till now in 4 different test sectors, beginning in 2010 with sector 5, and then sector 32. Only having those 2 sectors, we began our analysis and work on the paper describing this particular star. But along the work, 2 more sectors appeared in 2021, 2 consecutive sectors, which is also very, very good for the light curve analysis in sector 43 and 44. So here you can see in the right panel what the star looks like in the test observations. And the first thing that we noticed that there is a lot of different sources very close to our star, from which 2 plotted here in red also have their own 2-minute cadence test data available. So what we did, we calculated Fourier spectrum with the standard method described by Kurtz, and fitted 42 frequencies to the spectrum, and we adapted the criterion of signal to noise better than 4.0. For the 44 sector, the data was clearly the best in quality, and then we could fit even more frequencies in the number of 49. There is a clear evidence of pulsation in signal in light curve, and even the light curve itself suggests that there have to be some modes really close to each other, which interact between themselves, and that results in changing amplitudes of the modes between not only between sectors but also between different fragments of the light curve. And here you can see the sector 5 and 32 that we started our analysis on. After we fit those 42 terms, the residual signal is really not existent. Of course, data was cleared before and along the process. Some outliers were removed, which with bigger errors, and some faulty data is also present in all test observations, and we had to get rid of it in the beginning. 43 and 44 also looks very nice after fitting the frequency model. And when we take a look at the Fourier spectra, it clearly shows that somewhere between 1 and 2 cycles per day, the modes with highest amplitudes reside. As you can see, between sector 5 and sector 32, the maxima clearly change. And it's not only due to the fact that the modes are interacting between each other, but also due to the fact that we take different fragments of this interaction in the light curve, right? This is a different fragment of the whole interaction, and this is the different fragment. So clearly, in the consequence, we have to have different amplitudes for particular modes. In sector 43 and 44, data is even better, and we can clearly see that the maxima can be resolved better, and also are changing the shapes between the sectors. So having those first two sectors, we notice that one of the frequency number 9, is really changing its amplitude in a huge way, 200% less in amplitude between those two sectors. So we really thought that maybe it's not really a valid frequency, because it resides really close to the frequencies with high amplitudes. Maybe it's just a computational effect that just presents itself along the analysis. So first we think that this is not a real frequency, but when we took all the 4 sectors, it clearly showed that this frequency really matches the data in 43 and 44 sector. So we took it into account, and as I will show you briefly, it really plays a huge role in determining whether this star is really a B-type pulsar or not. So this F3 frequency is the dominant one, and it has harmonics. This is something somewhere about 1.83 cycles per day. And this is the dominant frequency in 4 observed data sets. So what we had to do with this data was to determine, is this a real pulsation signal in the 93 Tauri? Or maybe there is a secondary component which pulsates as a Gamma Doradus star, or maybe it's contaminated by the stars visible in the vicinity of our object. So first, we determined that those 2 bright stars, first one visible in the left bottom and the second one in upper right, have their own test data. We downloaded it, analyzed it, and what we got is that in the left star, the pulsational signal is clearly visible, but it's not visible in all the frequencies. It's only visible in the high amplitude modes. So it clearly comes from our star, not the other way around. And in the second star on the right does not have any signal from our star, but it has a lot of signal on its own, and it looks like some kind of delta Scuti or hybrid delta Scuti Gamma Doradus star in its own right. But we will not dwell on it here anymore. It's just to show you that the signal in our data does not come from these 2 objects. Also, we calculated the relative fluxes for all other stars in the field of view, marked with orange crosses and pink, I guess it's violet crosses and blue crosses, and it showed that there is a up to 1% flux for our star, so it would be impossible for the signal coming from those stars. Okay, and now if we now know that there is no contamination from the stars located in the vicinity, now we should think maybe there is a secondary component in the system. So it happened that this star was observed with VLT NICO survey in interferometric observations. And what they found that there clearly is some kind of secondary component there. So still, we cannot be sure that its the pulsations come from low amplitude B-type star or maybe higher amplitude A-type star or F-type star, which is present in the system. But with the help of asteroseismology, we can determine that the real variability really comes from the B-type star. So what our colleague Przemyslaw did, he fitted evolutionary tracks for different masses and for different frequencies that we fitted to our Fourier spectra model. And so it happens that it very nicely sits in the domain very well established for late type B-type stars. And I mentioned that this F9 frequency was really instrumental in doing so. If we didn't have this frequency, the whole project the whole concept would become much more problematic. But having the physics of SPBs, we also know that there should be some quasi-regular period spacings between oscillation frequencies, and this is also clearly visible in the bottom right panel in the figure 11, taken taken just plainly from our paper. So these are great evidences of the pulsations in the system, but coming from the B-type star. Okay, so now going to other objects that we have analyzed. We didn't hear is actually the work of my colleague Dr. Ewa Niemczura, who started the analysis of the newer sample provided by the selection made from Paulsen catalog and Gonzalez catalog. So here you can see some of the stars spectra from this catalog, and of course the manganium and mercury lines are very strong here. The same for Gonzalez catalog. And the age numbers presented here are not just by accident. These are the stars that I will present you in a moment in the form of light curves and Fourier spectra. So here are two panels that are presenting the chemical abundances for these stars that I will present. So this is the analog for the plot that I showed earlier for the stars analyzed from the first sample of 275 stars. We adopted evolutionary tracks and isochrons from CESTAM code, which comes from DIL 2018. The equation of state and opacities comes from OPAL project. Abundances, chemical abundances from Asplund 2009. And in this analysis, we are not using any magnetic field, no mass loss, and no rotation. So we are not using the newer instability domains provided by Walczak and Daszyńska-Daszkiewicz, but mostly dwell on the domains provided by Pamiatnik. Okay, so let's start with the first one. This is just the example of a single eclipse visible in the test data. Some stars clearly dwell in the binary systems, which we should expect, and this is the direct evidence of it. Of course, the Fourier spectra visible in the bottom panel is not really something to remember. It just shows that this signal is visible, but having one eclipse, Fourier analysis doesn't really fit the project. Also, we have then another star, HD 1279, which have some kind of variability seen in the lower frequencies, which may as well come from the gravitational modes, pulsation modes, which would be very much expected in the SPB stars. Here, going to the stars with much more interesting light curves, we can see another star which has a great two-minute cadence data. And when we take a look at the Fourier spectrum, we can clearly see some signal. Probably it's a dual effect combination of both rotation and pulsation. Another one visible here, and this one is available for 4 sectors, 2 pairs of consecutive sectors, which greatly enhance Fourier analysis. And when we zoom into the one sector, part of one sector, we can clearly see something happening here. And plotting it in the Fourier, we can see that this is a really, really strong signal in one of the modes. The spectral type, as well as the class, luminosity class, very well fits the SPB stars. It is a HgMn chemically peculiar star, and it was previously recognized or proposed by Ballona as a rotational variability, but Pedersen then also came to conclusion that it may be SPB as well. So did Kochukov just in the last during the last year. We found 11 independent frequencies with the amplitudes up to almost 0.3. It should be mini magnitude, of course. It's not magnitude, it should be mini magnitude. Another one here, but now we kind of don't have more stars with this high cadence, and this will be light curves presented for FFI photometry. This one clearly have some variability in the light curve, and when we do the Fourier analysis, we find something like the previous one, but when we take a look in the literature, it's SB2 star, but most probably it's a triple system with a third component on a really long orbit. 10 independent frequencies can be fitted here, 4 combinations and harmonics as well. Amplitudes also are very low, and it's also mini magnitudes, not magnitudes. I'm very sorry for that, but I think it's autocorrect from Keynote or from creating the description. So it's really low amplitude, but the signal is clearly visible. Okay, here are some other interesting objects which we right now think that they may be candidates for pulsational variability. Here are the 4 other ones, and 4 last. I think this one, yes, this one are the last ones. This one in the upper left panel is particularly interesting because it exerts this quasi-sinusoidal variability, and in itself it has some variability as well. So it may be an elliptical variability with pulsations visible in the system as well. So this is still work in progress to publish the analysis of all the HgMn stars visible in Tess. We have great sample of close to 300 right now. And as you can see here in the beginning of our variability table, there's a lot of different variability types presented in the data. Still work in progress. But in the last slide, I would like to leave you with the same question that we entered our project with. So why is that so few of these HgMn stars pulsate? This is the very unexpected effect. Clearly, it was shown that roughly half of them should pulsate with the 50, 20, 10 millimagnitude amplitude. We have here pulsational candidates with amplitudes of 1 or half a millimagnitude. So where are the other ones? Given that Tess is observing the entire sky and really probing very well all the different spectral types of stars, and there shouldn't be an observational effect here taking place. What is the reason why we do not have pulsations in these stars? Maybe there is a physical effect modifying the Z-bump mechanism or stabilizing the modes, possible modes of pulsations in the stars. And the question should be asked, what is the influence of slow rotation in the stars, and what is the influence of the presence of magnetic field? So what we would like to do next to finish up this analysis, publish the full variability search among HgMns, but in the future, maybe some ground-based multi-band observations for candidates would come in handy. Having different light curves in different bands really helps to identify pulsation modes, so that it would come in handy here. But in a few years, we will have more test data as well as Gaia light curves, which will also really enhance our resolution of our Fourier spectra as well. And we are now working on a better way to provide light curves from FFI photometry, applying differential image photometry to the data that we can download from the Tess archive. So all these findings I presented here in these presentations are included in two papers. One is accepted to be published soon in MNRAS about the 93 Tauri and asteroseismic analysis of it as well. And all targets are being prepared right now, and I think that this is the beginning of next calendar year should be published, hopefully, in the near future. So if you have any questions, I will be very happy to answer them right now. Thank you very much.
Dr. Mikolajczyk, we thank you for this very nice talk. Actually, it's a lot of work to research this much of sources and this much of data.
Yes.
So good luck also in your PhD defense. So is there any question from audience? It's, yeah. Tolga Güver.
Hi, how are you?
Hi, Tolga. How are you?
Good. Very nice talk. Thank you very much. Really interesting. I just wanted to, maybe I missed, I'm sorry if I did so. What really determines, or what do you think determines the amplitude of the oscillations? You showed some light curves, which show some like really nice sinusoidal variations. Some had. What is the physical mechanism that we think is behind this oscillation?
Yeah, the physical mechanism is just the same as in all the other pulsating stars. Like it's a heat valve coming from the over presence of electrons in one of the stellar layer. In classical pulsators like Cepheids or type 2 Cepheids or delta Scutis, this comes from the ionization, second ionization of helium. And some electrons also from hydrogen ionization. But in the case of late B-type stars and early B-type stars, which are respectively SPBs and beta Cepheids, it comes from ionization of the elements of iron group. So the temperature is hot enough, is high enough somewhere in the stellar interior. Its logarithm of temperature is 5.3, which translates roughly to about 200,000 degrees. And the ionization is clearly visible here in the panel, in the left panel, this Z bump. And as you can see in the case of 12 stellar 12 mass sun mass star, the Z bump is much higher, much more edgy than the bump coming from helium and hydrogen. Also, the stability of the modes, pulsational modes, can be obtained in the domain of helium and hydrogen, but the unstable modes that we want to have to pulsate the star, to change the physical interior of the star, to really change the size, change the temperature of the star, comes from the layer much deeper in the star.
Thanks, Mike.
Okay, is there any other question? It seems there is no any other question. So we thank you again for this very nice talk.
Thank you for having me. Thank you for having me. It's really nice to talk to you.
Yeah, and for all the others, see you in our next meeting.
Thank you very much. Have a nice day. Take care.
Have a nice day too.
You too. Bye.